Okay, so continuing on with some other trig equations of different types. These down here have something to do with factoring. So what we want to do on this one is you want to notice that this one is already set equal to 0, and it looks like you can factor a tangent x out of the left side, so that's what you want to do. And then this one is you're solving on an interval, so you're going to get specific answers to this equation in radians from 0 to 2 pi. Okay, so take a tangent out. You would have tangent x, then you would be left with sine x plus 1 equals 0. And then what you do is just set each individual factor and solve. So equal to 0. Tan x equals 0. We need to solve that equation by looking at the unit circle. Also sine of x plus 1 equals 0 on the unit circle. Okay, so what happens on this then is, remember the tangent is y over x. So we need to figure out where y over x is equal to 0 on the unit circle. So one place that happens is at the point 1, 0, because that would be 0 over 1, or that would be 0. So the tangent of 0 radians is 0. The other place it would happen is this point, where you would have 0 over negative 1 equals 0. So you got two solutions here, 0 and pi, to this equation. Okay, so that takes care of that. Okay, the next one, you want to add or subtract 1 from both sides, so you would get sine of x equals negative 1. So now the question is, where is the sine negative 1? It only happens one place, and that's at 3 pi over 2. Okay, so it looks like you've got 3 answers to this problem. So I'm just going to put this in a set brace. It doesn't matter what order they're in, 0 pi and 3 pi over 2. Okay, now one thing that's always worth showing, at least on some of these problems, is that a graphing calculator can actually check the answer to this problem pretty easily. So I'm going to put my calculator in radian mode and just show this to you. So we're going to graph just the original problem, which was tan x multiplied by sine x, and then plus tan x. All right, and then we're going to set this up. The window just needs to go from 0 to 2 pi since we're solving on that. So I'm going to go 0 to 2 pi. Not that. So 0 to 2 pi. Okay, you can scale by whatever you want to. Okay, I'm just going to scale by pi over 2, but it doesn't really matter. And then for the y's, I don't know, let's just try something like negative 5 to 5. Just kind of get all we got to do is get a view of this. Okay, so what I'm going to do now, when I graph this, we're going to find out what values of x make the graph equal to 0. So I'm going to trace out these answers and show you what happens. Our first answer was 0. So notice that y is 0 and x is 0, that point right there. The next thing I'm going to trace is pi. Notice when x is pi, y is 0, so that verifies that. And then the last answer was 3 pi over 2, so I just put in 3 pi over 2. Same thing happens, okay. I think I put the wrong thing in there, didn't I? Oh, yeah. There is something that I didn't notice on this problem, and I forgot to do this. You got to check your answer to this, and this is one of the benefits of doing this, is the problem is when x is 3 pi over 2, something happens on the tangent. Okay, so let me show you what would happen. Okay, well, there's a reason why that you're not getting y equals 0. It looks like you might be getting that on the graph, but the graph can be misleading. So what happens is, if you do the tangent of 3 pi over 2, okay, notice at 3 pi over 2, y over x is undefined. So you're undefined, so that means you have to throw out that solution. So there's only 2 solutions to this problem. Okay, so this one actually has to be thrown out. So that's called an extraneous solution. So sometimes you have to be really cautious about things like that. Okay? Okay, so the next one we can factor as well. So you have a cosine squared x minus cosine x equals 0. Okay, I can factor a cosine out. So that would leave me with cosine x minus 1. So you want to remove the common factor. And that's the same thing. We got two factors. So both of these individual factors need to be set equal to 0. So we would have cosine of x equals 0. And we would have cosine of x minus 1 equals 0. So now it's just a matter of interpreting on the unit circle. Now, unlike the last problem, we're not going to have any problem with an extraneous solution because the cosine's always defined. The thing that happened on the last problem is you had a tangent. And since the tangent of 3 pi over 2 is undefined, you had to throw that out. Right? So what happens here is, let's look at where the cosine is 0. So the cosine is 0 where x is 0. So that happens at two places. That happens at x equals pi over 2 and x equals 3 pi over 2. Okay, the second one, we add 1 to both sides. We get cosine x equals 1. Okay, the only place that happens is here when x is equal to 0 radians. Okay, so you would just get x equals 0. So this problem has three answers, 0, pi over 2, and 3 pi over 2. Now there aren't any extraneous solutions to this. I know that basically because the cosine is always defined. But you could do this as well. This is worth showing students. I'm just going to graph the original problem, and you'd have to go like this. On most graphing calculators, you would go cosine x in parentheses squared, and then minus cosine x. And then I'll just use that same viewing window I did on the last problem. And we got that, so we can trace out these three answers. So if I trace at 0, y is 0, so that proves that. If I trace at pi over 2, okay, that's giving me when x is pi over 2, y is 0. And finally, if I trace at 3 pi over 2, okay, that also verifies that. Okay, so those are the three right answers. The reason why 2 pi is not an answer is because 2 pi is not included because there's a parenthesis on that. So you don't want 2 pi as an answer. Okay, but notice on this, if I traced it 2 pi, what would happen is I get something that's not right. I must have put something in there wrong. So let me get back to where I was here. I think the reason it did that is because of the way I have my interval. This is going, x max is going to 2 pi, but it's only estimating it. That's the reason it's not accepting 2 pi when you trace it. Okay, so that happens sometimes on there. If I wanted to do this, though, if I wanted to just change this, not that, if I wanted to change this to 7, okay, let me show you what would happen now. Okay, the graph would go out a little further, and now if I wanted to trace it 2 pi, then I'd get 0. But my point that I'm trying to make is 2 pi is not an answer because it's outside of that interval. Okay? All right, so that's how that would work out. Now the next problem, I'm actually changing it. You could solve that problem with the tangent in it, but it would not factor, so you'd do a quadratic formula, and I've just decided to not test with a quadratic formula. You did some of that stuff with in your homework, so it's something you certainly want to know how to do. So I changed the problem to something that does factor. So we're going to factor this. We got one side set equal to 0. You always want to have that when you solve a problem by factoring. So basically the factoring goes like this. This is your first term. That's your last term. The middle term is the combination of inner and outer. So sometimes students struggle factoring trig expressions, which is kind of interesting. If you can factor the way you learned in an algebra class, it's really the same concept. So the first term, you're looking for two things that multiply to give 2 sine squared theta. So the nice thing about this, there's only one way to do that, is to have 2 sine theta and sine theta. Okay, like that. So that's got to be that if this thing's going to factor. The last term is -2. So also on this, there's just 2 and 1. Now it's going to turn out that the order you put this in is a real big deal. So let's try it this way as 1 and 2. Now the way I tend to teach this is I say figure out the signs at the end. So this would be 1 sine theta. This would end up being 2 sine theta, or no, not 2 sine theta. 2 times 2 is 4. So we would have 4 sine theta. What we're trying to get, nobody's home, bye. More calls from salespeople. I just hang up on them. All right, so let's see. What we do here then is we're trying to get a negative 3 sine theta. So we got plus minus like that. So I just have plus and minus, so that's the correct factoring. It's always a good idea to multiply stuff out, check it by FOIL, and see if you're on the right track. Now what you want to do is just like I've been doing on the previous problems, you want to set the first factor equal to 0, solve. That will end up being an interpretation of the unit circle. Same thing with the second factor like this. Okay? So on the first one, subtract 1 from both sides. You would have 2 sine theta is negative 1. You want to divide by 2. So that would be sine theta equals negative 1/2. So you're isolating the trig function. Now what you want to do is just take a look at the unit circle and interpret it. Okay, so let me slide the unit circle down here so we can see it okay. So there's 2 places on the unit circle where the sign takes on a value of negative 1/2. Okay, these 2 places occur at, they occur at 11 pi over 6 and 7 pi over 6. So that should be 2 answers to the problem. Is theta is 7 pi over 6 and also 11 pi over 6. Okay, so now we go to the next one. We'd add 2 to both sides, so we'd have sine theta equals 2. So you look on the unit circle and figure out where the sign's to. It never is. The biggest y, in fact, the biggest value of a sign is 1. Okay, so it's never going to be 2, so this has no solution to it. So then that just means your 2 solutions of this problem are 7 pi over 6 and 11 pi over 6. Okay, so those will be your 2 solutions to that problem. Okay? Okay, now working from here, if you want to check this on a graphing calculator, it's always kind of worth doing. I'll do this on this problem as well. Just go back to the beginning of the problem. We had 2 times sine of x squared, so that has to be put in like that. And then it was minus 3 sine of x. And then it was minus 2 like that. I'm going to use that same window I did on the last problem. That's kind of an interesting looking graph. We only got 2 answers. That's what the graphic calculator is showing you. These places here where you're intercepting the x-axis should be the answers. So I'm tracing at 7 pi over 6. Okay, when I do that, that checks. Y is 0. And if I trace at 11 pi over 6, okay, that also checks as well. Okay, so 100%. You can pretty well check graphically on these problems. Okay, now I'll move to the next stage here, and we're going to probably use some identities on some of these equations. Okay, so that's what these things have to do with, basically. Okay, so what happens on this is since you have that cosine of 2x, that makes you think that you want to do an identity. So there's 3 identities for this. The cosine of 2x, we've learned, is sometimes I can't write and talk at the same time. So the cosine of 2x is cosine squared x minus sine squared x. That's also the same as 2 cosine squared x minus 1. That's also 1 minus 2 sine squared x. So it's up to you which one you want to use, but the best one to use is this one because you already have a cosine in your equation. So you don't want to go with those other 2. It would work, but you would have to use another identity anyway. So it's best to use this. So what I'm going to do is substitute, change the cosine 2x to 2 cosine squared x minus 1. I still have the minus cosine x. is equal to 0. Now we're going to try to solve this one by factoring, so I'm going to put this in order, okay, like this, and then I'm going to try to factor this the way I've been doing the previous problem. So we got the first term, last term, and the outer and inner. So when you factor this, you want to make sure that you get your factoring right. The first term is 2 cosine squared x. So there's only one way to do that. Okay, you would have 2 cosine x times cosine x, and that's it. The last term is -1, so the only way to do that really is to go 1 times 1 to get 1. Okay, so I'm going to throw in here a 1 and 1. Now, again, I got to figure out how the signs go. Okay, so this inner term is cosine x. This outer term is 2 cosine x. We're trying to make this add up to negative cosine x. So the way to do that is to have a minus 2 cosine and a plus cosine. So we're going to have here, we want to have a positive here to get that positive cosine and a negative here to get that negative 2 cosine. Okay, so that's how you would approach that problem then, is you would want to do that. And then from here, what you would want to do is just set each factor equal to 0 like we've been doing. So we have 2 cosine x plus 1 equals 0. And we have cosine x minus 1 equals 0. Solve these two equations. So subtract 1 from both sides. You'll get this. Divide both sides by 2. You get cosine x equals -1/2. Okay, simple interpretation of the unit circle. The cosine takes on a value of -1/2. 2 locations on the unit circle, 2 pi over 3 and 4 pi over 3. So that's going to give you these two answers. Okay, and then the next one, we're going to add 1 to both sides. We get cosine x equals 1. The only place that happens is at 0. We have that. Okay, and whoops, hold on, that's not right. Yeah, that's right. Cosine is 1, that's the only place. So x equals 0. All right, so the three answers to the problem are 0, 2 pi over 3, and 4 pi over 3 like that. Okay, going to do a real fast check on this. All I'm going to do on this is just type in the problem, clear this crap off, or not crap, that's good stuff. Trig's good stuff. Okay, cosine of 2x minus cosine of x. Okay, I'm just going to graph that in the same viewing window that we've been doing. Okay, we got that. Let's see, what do we have? 3 answers, so let's trace them out and see on here. One of them, this answer here is probably, that's 2 pi right there. So if you trace it 0, that works. Trace it 2 pi over 3. Okay, that works. And trace at 4 pi over 3. That also works. Okay, now 2 pi is what this one is. So if you trace at 2 pi, well, that's too big anyway. Okay, because remember, we were solving on the open interval at 2 pi, so 2 pi doesn't count. Okay, so that's the idea. Okay? All right, next problem. Also, we have to use identities on this now. So what happens is we have 2 different trig functions. This thing does not factor. So we got sine squared x plus cosine squared x equals 1. Now, an interesting thing happens on this problem. I think I changed this on your thing too, but what would happen in this equation is you'd have 1 equals 0, so there would be no solution to this equation. I believe I changed the problem on your handout. That's okay. I mean, that's how you would solve that equation. That'd be easy. 1 is not equal to 0, there's no solution. Okay? So I think what I did, I think this had a typo on it. Although that's, how you would do that, so it's good, certainly good to look at. I think this problem was intended to be sine squared x minus cosine squared x equals 0. Okay? So again, you have to use an identity. We know that we have sine squared x plus cosine squared x equals 1. So you need to plug in, just get it down to one trig function. So it's up to you how you do this. I'm going to I think I'm just going to solve this for cosine. So if I move the sign over there, I would have cosine squared x equals 1 minus sine squared x. I could also solve for sine and plug that in. I don't know. It doesn't matter which way you do it. So I'm going to leave the sine squared alone, and I'm going to replace the cosine squared with what it's equal to. The cosine squared is 1 minus sine squared x. Okay, now if you do it this way, be sure that you're real careful about putting that in a set of parentheses. So what I'll have now is sine squared x minus 1 plus sine squared x is equal to 0. Okay, these are like terms. Sine squared plus sine squared is 2 sine squared x minus 1 equals 0. Okay, so what I'm doing is I'm getting that down to one trig function so I can solve it. Okay, there wouldn't be any other really good way of doing this problem. Okay, so the idea with this is add 1 to both sides, so we'll have 2 sine squared x equals 1, divide by 2, so we get sine squared x equals 1/2. You want to now do the square root property, and when you do this, you end up getting sine of x is equal to plus minus, and that would be 1 over root 2, which would rationalize to root 2 over 2. So you would end up interpreting the unit circle, and you'd have to do two things. You'd have to figure out, okay, where is the sign positive root 2 over 2, and where is the sign negative root 2 over 2. So you're going to get 4 answers to this trig equation for that reason. Okay, so now what I'm going to do basically is this. I'm going to look at the unit circle. Okay, it's root 2 over 2. The sign takes on that value 2 places, pi over 4 and 3 pi over 4. So here we would get these 2 answers. Okay, the sign takes on a value of negative root 2 over 2 in these 2 locations. So that is 7 pi over 4 and 5 pi over 4. So there's your other 2 answers, would be x equals 5 pi over 4 and 7 pi over 4. Okay, so you end up getting 4 answers. Doesn't matter what order you put them in. I'm just going to put them in the order of smallest to largest, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So what's happening, there's kind of a nice pattern on this too. They're going by odd numbers. All right, so it's just you're always going to have an answer of odd pi over 4, you know, throughout the circle as many laps as you go through. So those would be the 4 answers to that problem, okay? And that could be checked on a calculator like this basically. If I go parentheses cosine x squared, and then it was minus parentheses cosine x squared, up. Come on, teacher. Sometimes I just don't pay attention to what I'm doing. Okay, that should have been sine x. There we go. All right, now we got it. Graph it. Let's see if we got 4 answers. You do. 1, 2, 3, 4. Like that. Okay, so from here to here. 2 pi is right here. So if you trace them out, you would have the right answer. I'm not going to do that, but if you traced all those answers, you would get 0. Okay? All right, now we're going to get into the multiple angle problems. And there's probably 2 ways you could actually do this problem. You could actually solve this problem with a cosine double angle identity, but what I'm going to do when you have multiple angles like 2x and 5x, oftentimes it's a good idea to use this strategy. So what I'm going to do, the first thing I'm going to do is I'm going to do the inverse cosine of both sides of this equation. Okay, you got to kind of follow this procedure precisely, and this will kind of tell you what to do. So the left side would just be 2x, and then the right side, well, what we need to do on this is we need to find on the unit circle where the cosine is 1/2. And the cosine is 1/2 at 2 places, and that would be at pi over 3 and 5 pi over 3. Now, you're not really looking at the range of an inverse cosine. We're just trying to figure out where are the places on a unit circle where the cosine takes on a value of 1/2. So there's actually two things. What we would say is the first answer is pi over 3, but the period of a basic cosine is 2 pi k, where k is an integer. Okay? And then the second answer would be 2x equals 5 pi over 3 plus 2 pi k, again where k is an integer. So what you would need to do is solve these two equations. The directions to the problem say all real solutions, real means radians, all means formula. So we're going to multiply both sides by a half, okay, like this. When we do that, the 2's will wipe out. We're going to have x equals pi over 6 plus pi k, where k is an integer. Okay, again, the 1/2 of 2 pi, see I'm just multiplying straight across, so that's pi over 6, and then half of 2 is 1. So that would actually be one formulaic answer to that problem. We do the same thing over here. We multiply both sides by a half and multiply that out. So what we would end up having is x equals 5 pi over 6 if you multiply that out. And then half of 2 pi is just pi k. Again, k is an integer. So you got to write these two answers to the problem. That gives you a formula for all of the solutions. Okay? So that's the general strategy that you do when you have a multiple angle like a 2x or a 3x or even a half x or a third x, something like that, where you have a period change. And I want you to notice that the pi k is kind of important to make this connection. The pi k is the period of cosine of 2x. So if you were graphing cosine of 2x, you would do 2 pi over 2, so you'd get pi. Okay, so that would be the answer. Okay, the next problem you'd approach the same way. Now, if you want to, what I would probably recommend that you do is just go ahead and change this to a tangent. Okay, you don't have to, but you could. All right, so we can just do it like this, or let's just leave it alone. Maybe we'll just leave it alone. So let's do an inverse cotangent of the cotangent of 5x. Let's just do that to both sides. You could change this to a tangent also. I think the benefit of staying with the cotangent, though, is we might end up with something being undefined. I don't think it'll be a factor on this problem, but it's a good idea to just stick with the original. So this would be 5x on this side, and this should be, I should have written down the cotangent of square root of 3. So we have 5x equals the inverse cotangent of square root of 3. So what you want to do on your unit circle now is you basically want to go on here and just look at, remember the cotangent's x over y, so we're looking at where x over y is the square root of 3. That actually happens two places. It happens here because you would have square root of 3 over 2 over a half, which is square root of 3. So that would be one solution, would be pi over 6. It also happens here. Okay, if you did x over y, you would have negative root 3 over 2 divided by negative 1/2. That also is square root of 3, so it happens there as well. So what we would have is, we would write this like this now, as we would just write this as 5x equals, the first answer is pi over 6. Now the period of a cotangent is pi k, not 2 pi. Okay, then you would get this second answer, which we write as 5x equals 7 pi over 6, again, plus pi k. All right, so what we'd do is we'd solve these equations. So we would want to multiply both sides by a fifth here. Okay, and that would cross that out. That would give you one formula, would be this. This would be x equals pi over 30 plus pi over 5 k, where k is an integer. So that would actually be one answer problem. Okay, that actually is the answer of the problem, and I'll explain why. If you went over here, what happens is this is unnecessary. If you went through and multiplied this by both sides by a fifth here, you would end up basically getting this. You would get x equals 7 pi over 30 plus pi k over 5, if you want to write that way, with k being an integer. The thing about this is I want you to notice this. The reason this is unnecessary is if you take this first answer, pi over 30, and you add pi over 5 to it, so like if k is equal to 1, if you got a common denominator on this, you would have pi over 30 plus 6 pi over 30, so you would get 7 pi over 30, which is this. So that turns out that answer is not necessary. You only need one formula, and that will give you all of your answers. So that would be the only formulaic answer to that problem. Okay, all right, let's move to the next page here. Okay, so the next page, I want to kind of finish up the trig equation thing, and then this will be the third part of the video. So with this one right here, you want to start by adding 1 to both sides. So your first step is isolate the sine function. So we would have this equals 1. You would want to divide by 2, so you would end up having sine 2x equals a half. Okay, isolate. Okay. Second thing is you want to do the inverse sine of both sides. This is a multiple angle equation, so we're going to take the inverse sine of both sides. And do this. So what we'll have is this would be 2x. Now we need to look at the unit circle. There's 2 places where the sine is a half. That happens at pi over 6 and 5 pi over 6. So we're actually going to get 2 formulas for this. So we're going to have 2x equals pi over 6. Now again, what's the period of a basic sine of x? 2 pi. To start with, we're going to say 2 pi k, where k is an integer. Okay, then the other answer is 2x equals 5 pi over 6. And again, we'll say plus 2 pi k. Okay, and let's see, we know that k is going to be an integer. So we're going to solve these 2 equations, multiply them by a half on both sides over here. Okay, that will give you the formula x equals pi over 12 plus pi k. All right, so again, I'm just multiplying straight across. I'm taking half of 2 pi, which is pi. I do exactly the same thing over here. Multiply both sides by a half. And what I'll get here is I'll get x equals 5 pi over 12, and then plus pi k, where k is an integer. Okay? Now, that is not the answer to the problem, because we're not looking for a formula. We're looking for all of the answers from 0 to 2 pi. So the third thing that you want to do is this is where you just start varying the value of k. So if k is 0, you can do this in your head. Just look at these 2 formulas. If k is 0, that will wipe that out, and that will give you an answer of pi over 12. And if you go to the next one, the next formula, if k is 0, that wipes this out, and that gives 5 pi over 12. So that's how that goes. Now, all you're really doing on this is just adding the period. So if k is equal to 1, then what you'll end up having here is this. You'll just end up having pi over 12 plus pi, like that, because if k is 1, you're just adding pi. And that's all you're going to do is just keep adding pi to the answers over and over again. So if I get a common denominator, that would be pi plus 12 pi. That would be 13 pi over 12. So that's an answer. You do the same thing over here. K is equal to 1. So you take 5 pi over 12 plus pi. Again, you can get a common denominator. So what you're really going to do is the numerator is just going to keep going up by 12. So you would get another answer, which would be 5 plus 12 would be 17 pi over 12. So you would end up getting these 4 answers to the problem. Now, if you went on, and let me kind of show you how this goes. This is what I like students to be able to do on these problems, is just sort of count these things out. So here's how the answers go. You have pi over 12, and then this just goes up 12. So you have 13 pi over 12. Then up 12 would be 25 pi over 12. But see, that's bigger than 2 pi, so you don't use that answer. And then the next answer would be 5 pi over 12. The numerator goes up by 12 to give 17 pi over 12. If you went up 12 again, you would have 29 pi over 12, which again is bigger than 2 pi, so you don't use that answer. So your answers to the problem are going to be pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Okay, that's the answers to the problem. Okay, you just don't want to go too big, so you don't need to go to k equals 2 on this problem because you would start getting answers that are too big. And another thing you can do on this, like any of these equations, it's pretty easy to check your answer. So if I just graph 2 sine of 2x minus 1, we would have learned how to graph this kind of thing in this class. Just have an amplitude of 2, period of pi, down 1. So let me show you that we have 4 answers. The 4 answers are here. 1, 2, 3, 4. This one is bigger than 2 pi because 2 pi is right here. Okay, so you can just trace them all out. I'll just trace a couple of them out. Pi over 12. Okay, that verifies that that answer is okay. You can do 5 pi over 12. And that will verify that that one's okay. And then 13 pi over 12. Okay, that should verify the third one. That's right. And then finally, if we do 17 pi over 12, then that verifies the fourth answer. Okay, so like any of these, you can check on your calculator. Okay, so let's go ahead. I'm going to wrap up with these 2 problems. These are not unit circle problems because of these 2 numbers. So these are calculator problems. So what you're really doing on this is you can kind of do the same strategy I did on the last problems. You can just do the inverse cosine of both sides. That's what you have to do on your calculator. And your calculator is only going to be kind enough to give you one answer. So first of all, on this one, your calculator must be in radians because it's asking for a radian answer from 0 to 2 pi. So what I'm going to do is inverse sine of 0.826, and this is going to give a reference angle in radians. So that's going to give approximately 0. And I'm just going to round to like 2 decimals, 0.97. So that would be one answer to the problem, but there's another answer, and what you have to realize is this is usually the hardest part of the problem for students. We're solving a cosine. Remember, a cosine is positive in quadrants 1 and quadrants 4. So what we have is the quadrant 1 answer in radians. So that is a reference angle. We also have that same reference angle for quadrant 4. So what you do is quad 1, the calculator gave us the quad 1 answer. The quad 4 answer, well, you got to go like this. You go all the way around the circle, which is 2 pi, less that. So you go 2 pi minus 0.97 to get the other answer. That's the part of the problem that sometimes students don't get. Okay, I mean, it's just because it's in radians. If it was in degrees, I think students understand it better. So anyway, I just do the same thing. I just do, if it was degrees, we'd do 360 minus that angle. Okay, so that would just give me, the second answer would be about 6.48. So my 2 answers to the problem are about 0.97 and 6.48. Okay, this problem is actually real easy to check on your calculator. You just graph a cosine, which, we know what the graph of a cosine looks like. Well, just trace out your 2 answers. So if you trace out 0.97, whoops, got to get to my graph. If I trace at 0.97, let me show you what happens. Well, you get Whoa, 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 whoa. Did I do the right thing there? Did I craft the right thing? Yep, okay, so hold on just a second. Well, crap, I wasn't paying attention on this. Let me do this again, okay? I got the wrong original answer, so crap, I just continue to do stupid stuff like this sometimes. All right, just not paying attention. All right, so, okay, what I did on the calculator, I did the inverse sine of that. I should have done the inverse cosine of 0.826. But, you know, the reason I keep going through and checking these things is that's how I catch my careless mistakes I make sometimes, and you can do the same thing. So if I do this, I'm going to get this. So that quadrant 1 answer is going to be about 0. Let's just call that 0.60. So you would have reference angles of 0.60. So you'd do the same thing. You would do 2 pi minus 0.60 to get that other answer. Now we'll check it and verify it on the calculator. So 2 pi minus 0.6 is going to give the other answer, which is about 5.68. Okay, so let's see if that's better. I essentially solved the problem for sine of x. So we have 0.6, 5.68. All right, now let's graph. Let's check now. This is the cosine graph. And then if you trace at 0.6, well, what will happen is, see, the original problem was 0.826. So this is close to 0.826. We rounded on that, okay? That's okay. It's not equal to 0. It's equal to 0.826. The other answer was 5.68 radians, so that should give about the same. So since we rounded, we're fairly close, okay? So that's how you would check the answer on that. Okay, so I'll go ahead and do this last problem. I'll do this the same way with the calculator. So I'll do the inverse tangent of both sides of the equation. You don't really have to show this step. You can just immediately do the inverse tangent of 2.9. So anyway, you would get x equals inverse tangent of 2.9, which is a positive number. So I would have to go to my calculator, and I would have to do this. I'd have to, in radian mode, go inverse tangent of 2.9 and record this reference angle. So that actually gives x is about, let's just round that to 1.24. Okay, so what happens is the tangent is positive in 1 and 3. All we got was the quadrant 1 answer. So I'm going to just kind of write this as a reference angle of 1.24. All right, so what we have is we have this reference angle also of 1.24. So you end up doing this problem this way. The quadrant 1 answer is what the calculator gave. The quadrant 3 answer, just think about it. It's halfway around the circle pi plus that reference angle. So we do pi plus 1.24. So if I do that on the calculator, I'll just do pi and plus 1.24, and that will end up giving about 4.38. So it looks like the two answers to this problem are approximately 1.24 and 4.38. Okay, and then we'll do just a real quick check on the calculator to make sure the professor didn't do anything careless like he did on the last problem. So again, all I'm going to do is I'm just going to graph the tangent. We know what the tangent x graph looks like, so here's the tangent graph. And I'm just going to trace these two answers. So if I trace at 1.24, we just need to see that y is about 2.9. Okay, and that's correct. The second answer was 4.38, and that needs to be y is about 2.9, and it is. That's it. Okay, so those are the right answers to that problem. Okay. All right, so I'm going to stop here as the third part of the video, and then the rest of the video we'll do the oblique triangle stuff.